Welcome back to Sleepy Orbits. Maybe the lights went off an hour ago and sleep never followed you down. Maybe you're just home from a shift that ran long and the house feels too quiet in the wrong way. Either way, you're in the right place. Tonight, we're going to take the journey to the nearest star. It's called Alpha Centauri, and it sits about 25 trillion miles from where you're lying right now. The fastest machine human beings have ever launched would need roughly 75,000 years to cover that distance. You've probably heard that Alpha Centauri is our next-door neighbor, the closest star system in the sky, the obvious first stop on humanity's way out into the galaxy. But here's the thing most people don't realize. The word closest is quietly lying to you. The nearest star is so far away that it defeats every machine we have ever built, every engine we have ever imagined, and very possibly every generation of human beings who will ever live. Tonight, we're going to board a ship that doesn't exist and make the crossing anyway, and somewhere out there in the dark between the stars, the word close will stop meaning what it meant when you lay down tonight. One thing before we begin: if you fall asleep partway through, good. That's the point. In the morning, tell me in the comments the last thing you remember hearing. And if you make it to the end, tell me which part of the journey to the nearest star stayed with you and what you'd like us to explore next. If these nights help you rest, a like or a subscribe helps this channel more than you'd realize. Now, let's begin. Let's do something impossible. Let's leave tonight. While the rest of your street is asleep, you step aboard a ship, and we'll be generous with it. We'll give it the speed of the fastest object our species has ever flown. In December of 2024, a spacecraft called the Parker Solar Probe fell around the Sun at just over 192 kilometers every second. That's about 692,000 kilometers per hour, or 430,000 miles per hour. Nothing made by human hands has ever moved faster, so that's your cruising speed tonight. You leave Earth at the pace of our all-time record, and you hold it, without slowing, without stopping, forever. At that speed, the moon goes by in about half an hour. The Apollo astronauts needed 3 days to make that trip. You make it before your tea goes cold. In under 5 days, you could cross the gap to Mars at its closest approach, a journey that takes our real spacecraft about 7 months. In 5 weeks or so, you pass the distance of Jupiter. In 9 months, Neptune, the outermost planet, a crossing that took the Voyager probes 12 years. In about 10 months, you reach the distance of Pluto and the Kuiper Belt, the ring of frozen dwarf worlds at the solar system's edge. The New Horizons probe, the fastest launch in spaceflight history, left Earth in January of 2006 and needed 9.5 years to make that same trip. You've done it inside one. The entire solar system that every schoolchild memorizes, every planet, every moon, every world with a name, is behind you in well under a year. And here is the first uncomfortable number of the night. At the fastest speed any human object has ever achieved, your journey to the nearest star has now covered almost none of the distance, not 1%, not 1/10 of 1%. After 9 months of flight at 692,000 kilometers per hour, you have covered roughly 1/1000th of 1% of the way to Alpha Centauri. Keep going. In about 3 years, you cross the heliopause, the boundary where the sun's wind gives way to the thin gas between the stars. This is the line that Voyager 1, launched in 1977, needed 35 years to reach. In your 5th year, you catch and pass Voyager 1 itself. Take a moment as it goes by, because that small tower of gold foil and aluminum is the farthest thing humanity has ever sent. The farthest, after very nearly 50 years of falling outward through the dark. Later this year, in November of 2026, Voyager 1 will do something no human object has ever done. It will reach a distance of 1 full light day from Earth. 1 light day. The distance light itself, the fastest thing that can exist, covers between one midnight and the next. It took us half a century to push one small machine, 1 light day, out. The star you are traveling toward tonight is more than 1,500 light days away. Voyager, for all its glory, has covered less than 1/1600th of the distance you have to cross. And now the solar system is gone behind you. The probes are gone. Every marker with a human name on it is gone. And the honest arithmetic arrives. At your speed, the record speed, the speed no crewed ship has come within 100th of, the crossing to Alpha Centauri takes about 6,500 years, 66 centuries. And that number is the optimistic one, the fantasy number, because the Parker Solar Probe only touched that speed for moments, deep in the sun's gravity, falling like a stone around a fire. It could never hold it in a straight line. A real ship, coasting the way our real machines coast, moves like Voyager. And at Voyager's speed, 17 kilometers per second, the journey to the nearest star takes about 75,000 years. 75,000 years. Let that number sit there in the dark for a second, because it's the true weight of tonight's story. All of recorded human history, every empire, every war, every book, every name we remember, spans about 5,000 years. The journey to our nearest neighbor, one way at the speed of our farthest traveler, is 15 times longer than everything that has ever been written down. The last time 75,000 years passed on this planet, modern humans were still in the middle of their long walk out of Africa. There were perhaps a few 100,000 of us in the world. Every language spoken tonight, every alphabet, every god, every nation, everything you have ever heard of arose inside a span 1/15th as long as this single one-way trip. If a crew had launched back then, at Voyager's speed, aimed perfectly at Alpha Centauri, they would still be on their way tonight. They would not arrive for thousands of years yet, and no message they sent home would find anyone who remembered why they went. So how did we get here? How can the nearest star, the closest one in an entire galaxy of hundreds of billions, be so far beyond reach that the numbers stop sounding like travel and start sounding like geology? That's the story of tonight. And it begins with the distance itself, because the distance is the villain of this story. And like all good villains, it wears a disguise. The disguise is a small, friendly number, 4.24. Alpha Centauri is a triple star system, and its faintest member, a little red star called Proxima Centauri, is the closest individual star to our Sun at 4.24 light years. Say it out loud, and it sounds almost cozy. 4.24. It fits in a sentence. It's smaller than the number on your thermostat. Astronomy textbooks print it next to words like neighbor and doorstep, and every one of those words is technically true and quietly misleading. Because a light year is not a small thing. A light year is the distance light travels in 1 year, and light is not fast the way a plane is fast, or a bullet is fast. Light is fast the way nothing else in the universe is or ever can be, moving at just under 300,000 kilometers every second. In the time it took you to hear that sentence, a beam of light went around the Earth more than 30 times. 1 light year, one single unit of that little number, works out to about 9.5 trillion kilometers, or roughly 6 trillion miles. Multiply by 4.24, and you get the real distance to the nearest star. About 40 trillion kilometers, about 25 trillion miles, 268,000 times the distance from the Earth to the Sun. Numbers that size don't mean anything to a human mind, and they're not supposed to. Our brains were built to judge the distance to the far side of a valley, not the far side of a light year. So, let's shrink it until it fits. Imagine the entire solar system, the Sun, all 8 planets, everything out to Neptune, compressed down to the size of a basketball. One basketball resting at the center line of a football field, holding everything humanity has ever touched. On that scale, Earth is a speck of dust near the middle. Voyager 1, our farthest emissary, our proudest distance after 50 years of continuous flight, has made it about 0.5 meter from the ball. Now ask where the nearest star is. On this scale, with our whole solar system shrunk to something you could hold in your hands, Proxima Centauri is another basketball sitting roughly 7,000 kilometers away. That's the distance from New York to Rome. 2 basketballs on opposite sides of the Atlantic Ocean, and between them, nothing. Not a smaller ball, not a pebble, not a grain of sand. An ocean of vacuum crossed by no road, marked by no milestone, warmed by no fire, all the way from one shore to the other. And it truly is nothing, in a way that nothing on Earth ever manages to be. We say a desert is empty, but a desert has sand and wind and a horizon. We say the deep ocean is empty, but it's full of water and pressure and life. The space between the stars holds about 1 single atom in every cubic centimeter. The best vacuum chambers ever built in laboratories on Earth are crowded compared to that. If you scooped up a volume of interstellar space the size of the Earth, all the matter inside it would weigh less than a few grams. Between our Sun and Alpha Centauri, there are no known planets, no way stations, no islands, nothing to slow down for and nothing to aim at. Just 40 trillion kilometers of the emptiest emptiness that exists. That's what the friendly little number is hiding. 4.24 light years is not a distance in the sense your mind understands distance. It's an abyss with a name. If the basketball didn't do it for you, try weighing the trip in familiar vehicles, because this is where the number stops being astronomy and becomes something almost funny. Suppose you decided to walk to Alpha Centauri, a steady walking pace, never sleeping, never stopping. The trip would take you roughly 900 million years. When you set out, there would be no trees on Earth, no animals on land, almost nothing living outside the sea, because that's how long ago 900 million years was. Take the car instead. Highway speed, day and night, no fuel stops. About 45 million years. You would need to have started driving in the age just after the dinosaurs died, and you'd be pulling in about now. A jet airliner cruising at 900 kilometers per hour makes the crossing in around 5 million years, which is longer than anything resembling a human being has existed. Even a rifle bullet fired tonight and flying straight and true would take well over 1 million years to arrive. Every vehicle in human experience pushed to absurdity dies somewhere in deep time, long before the far shore. There has only ever been one traveler that makes this trip look easy, and it's the one delivering the star to you right now, at this moment, for free. Light. Part of the reason the disguise works so well is that you can see Alpha Centauri with your naked eye. If you stand outside on a clear night in the southern hemisphere in Sydney or Santiago or Cape Town, it's one of the easiest stars in the sky, the third brightest star of the night, a brilliant point in the constellation of the Centaur. Sailors used it to navigate for thousands of years, and your brain, looking up at it, runs a piece of ancient software. Bright means near, dim means far. On the savannah where that software was written, it worked perfectly. A bright fire is a close fire. A faint fire is a distant one. But pointed at the stars, the old rule fails completely, and it fails in a way that matters for tonight's story. Alpha Centauri looks bright not because it's grand, but because it's near. And near, in the language of stars, still means a distance that breaks every machine we own. The star system your eye finds so easily, so casually, as if you could row to it, is 40 trillion kilometers of hard vacuum away. Your eye can touch it in an instant. Nothing else of you ever will. Here's a strange detail. When astronomers first measured that distance, they didn't believe it either. In the 1830s, a Scottish astronomer named Thomas Henderson was working at an observatory at the Cape of Good Hope, at the southern tip of Africa. He spent years making painstaking measurements of Alpha Centauri's position, watching for the tiny apparent shift the star makes as the Earth swings from one side of its orbit to the other. That shift is called parallax, and it's the same trick your own two eyes use to judge depth. Hold a finger in front of your face, close one eye, then the other, and the finger seems to jump against the background. Henderson was doing that with the entire orbit of the Earth as the space between his eyes. The shift he measured for Alpha Centauri was less than 1 second of arc, about the width of a coin seen from several kilometers away. When he worked out what that meant, the answer was so enormous, trillions upon trillions of kilometers, that he hesitated to publish. He sat on the result for years, worried he'd made an error. And in the meantime, a German astronomer named Friedrich Bessel announced the first published stellar distance to a different star in 1838. Henderson's measurement of our nearest neighbor followed in 1839. Think about what that moment was. For all of human history, the stars had been lights on a dome, close enough to hang myths on. And then, within 2 years, they became suns, and the nearest of them was revealed to be 25 trillion miles away. The sky didn't change that night. The sky had always been like this. We were the ones who suddenly knew how alone we were. Since Henderson's day, we've measured the distance to Alpha Centauri with almost absurd precision. Space telescopes can now pin down stellar parallaxes to millionths of a second of arc. We know how far away the nearest star is to a precision most laboratory instruments would envy, and none of that precision brings it 1 kilometer closer. This is the quiet distinction the textbooks skip past, the difference between nearest and reachable. In everyday language, those two words live next to each other. The nearest gas station is one you can drive to. The nearest hospital is where the ambulance goes. Nearest implies accessible. It implies an errand, a trip you could make if you had to. Alpha Centauri is the nearest star, and it is not reachable, not by anything we have built, not by anything we are building, not by anything currently on any drawing board of any space agency on Earth. Both facts are true at once. It's close enough to see with your bare eye, close enough to measure to a dozen decimal places, close enough that we already know it has planets, and it is far enough that no spacecraft that exists or is planned could arrive there in less than tens of thousands of years. The nearest star in the entire sky is, by every engineering standard we have, nowhere. That's not a paradox. That's just what the galaxy is like. We live inside a scale so large that seeing and touching have come apart. There's one more way to feel the distance honestly, and that's to climb the ladder of light. Light is the fastest messenger there is, so watch how long the universe takes at its own top speed. Light from the moon reaches you in 1 1/3 seconds. Moonlight is 1 heartbeat old. Light from the sun takes 8 minutes and 20 seconds. So the sunshine on your face at noon left the sun before you looked up. Light from Mars takes anywhere from about 4 to 20 minutes, which is why the engineers who drive the rovers can never use a joystick. They send the day's instructions and wait. Light from Neptune takes about 4 hours. Light from Voyager 1, our farthest machine, takes nearly a full day now, which means that when engineers on Earth send it a command, the round-trip conversation takes almost 2 days at the absolute speed limit of reality. That's the edge of everything we've ever touched. One light day, 1 day of travel for the fastest thing that can exist. And the light arriving tonight from Alpha Centauri has been traveling for 4 years and 3 months. The photons landing in your eye, if you went outside and found it in the sky right now, left that star in the early part of 2022. You are not seeing Alpha Centauri tonight. You're seeing history 4 years deep. Every star you have ever seen is a memory by the time it reaches you. The nearest one is the freshest memory in the entire sky, and even it is years old. So let's get back aboard the ship, because the ship makes all of this physical. When we left it, you were 5 years out, passing Voyager 1, moving at the record speed of the human species, and the solar system was shrinking behind you into a bright point. Here's what happens next, and I want you to notice how the milestones change. In your first year, the milestones came every few days. The Moon in half an hour, Mars in under a week, Jupiter in 5 weeks, Neptune in 9 months. Now they come like this. After about 50 years of flight, you cross the inner edge of the Oort cloud. This is the Sun's outermost territory, a vast, sparse shell of icy bodies, trillions of them by some estimates, left over from the birth of the solar system, drifting so far from the Sun that their year lasts millions of hours. This is where the long-period comets come from, the visitors that swing through our skies once and vanish for ages. And here is the fact I'd like to leave under your pillow tonight. At the speed you are traveling, the record speed, you will not leave the Oort cloud again for roughly 25 centuries, 2,500 years, just to cross the Sun's own front yard. At Voyager's real speed, it's far worse. NASA's own estimate is that Voyager 1 will reach the inner edge of the Oort cloud in about 300 years and will not pass beyond the far side of it for perhaps 30,000. 30,000 years to leave home. Not to arrive anywhere, just to leave. Try to inhabit that stretch of the journey for a moment, because this is most of the trip. This is almost the entire trip. And nothing happens. There's no wall at the edge of the solar system, no sign, no sensation of crossing. Outside the window, the view tonight is identical to the view a century ago and a century from now. The sun behind you has faded year by year until it's just the brightest star in one half of the sky, and then not even that, just one more point of light among thousands, and you'd need a star chart to be sure which one it was. Ahead of you, Alpha Centauri is a point that refuses to grow. You could fly for 1,000 years and it would look exactly the same. The nearest comet nucleus might pass within a few 100 million kilometers of you once in a generation, invisible, unlit, colder than any winter, and that would be the most significant event of the era. This is what the distance between stars is actually made of. Not adventure, not danger, mostly just time in quantities no living thing has ever experienced, time so deep that the journey stops being a journey at all and becomes something more like a fate. And while you drift through those silent centuries, think about what's happening back on the bright little world you left. In the first 300 years, roughly the time it takes just to reach the Oort cloud at Voyager's speed, everything you'd recognize expires. 300 years ago tonight, there was no United States, no electricity in any home on Earth, no photograph had ever been taken, no train had ever run, and no human voice had ever been recorded. Whatever the world looks like 300 years from now, it will be at least that unrecognizable to you, and your ship will still be inside the sun's own cometary halo. Go further. By 10,000 years, you're beyond the age of every institution that has ever existed. The oldest continuously used buildings on Earth are temples about that old, and we don't know what songs were sung in them or what their builders called themselves. Languages turn over completely on scales of mere centuries. English as spoken tonight would be as foreign to your descendants as the speech of the first farmers is to us, which is to say, lost entirely. By the time your ship finally clears the Oort cloud, the mission that launched you will not be remembered imperfectly. It will not be remembered at all, unless civilizations far more durable than any yet built choose, deliberately, generation after generation for thousands of generations, to keep telling one particular story about one particular light in their sky. The ship sails on either way, indifferent, patient, a message in a bottle from a sender who has long since become a myth. Here's the strange footnote to all of this. Humanity has already launched its interstellar fleet. It exists. 5 spacecraft, right now, tonight, are traveling fast enough that the sun's gravity can never call them back. Pioneer 10 and Pioneer 11 launched in the early 1970s, both long dead, both falling silently outward forever. Voyager 1 and Voyager 2 still faintly whispering. And New Horizons, the Pluto explorer still awake and climbing, 5 machines permanently leaving, and not one of them is aimed at a star. They were built to visit planets, and their escape routes point wherever the last planetary encounter happened to fling them. Pioneer 10 is drifting in the general direction of the star Aldebaran, and if nothing disturbs it, it will take about 2 million years to pass that neighborhood. Voyager 1's first stellar rendezvous, that distant brush past a small red star, is 40,000 years away. These are our actual, existing interstellar missions, unplanned, unpiloted, and unhurried beyond all meaning. And because their builders understood exactly what that meant, they mailed letters along. The pioneers carry engraved plaques, a man, a woman, a diagram of where their makers lived. The Voyagers each carry a golden record holding greetings in dozens of languages, the sound of rain, a heartbeat, a kiss, 90 minutes of music. Nobody involved believed anyone would ever find them. The records were made because the ships were going anyway, and it seemed wrong to send them empty-handed. Think about what that means. The only vessels our species has ever dispatched to the stars carry no crew, no engine for the journey, and no destination. Just portraits and songs, drifting on headings chosen by gravity, on voyages measured in millions of years. That is the entire interstellar fleet of planet Earth. 5 bottles thrown into an ocean 4 light years deep by people who knew they would never hear the splash. By now, a reasonable voice in your head is asking the obvious question. Fine, the distance is enormous, so go faster. We're clever. We split the atom, we left footprints on the moon, we flew a helicopter on Mars. Surely the 75,000 years is just an engineering problem, the way crossing the Atlantic was once an engineering problem. So let's take that voice seriously. Let's open the drawer of every engine humanity has ever built or seriously designed and point each one, in turn, at the nearest star. This is where the story stops being about a big number and starts being about a wall. Start with what we actually fly, chemical rockets. Every rocket that has ever carried a human being has worked the same way, burning fuel in a chamber and throwing the exhaust backward. It's the technology of the Saturn V and the technology of every booster flying today, refined for a century, and it has a hard ceiling built into the chemistry itself, because the energy you can squeeze from burning a kilogram of fuel is fixed by the strength of chemical bonds, and it is not much. The fastest any human beings have ever traveled was aboard Apollo 10 in May of 1969, when the returning capsule hit almost 40,000 kilometers per hour, about 11 kilometers per second. That's the crude speed record, and it has stood for more than half a century. At Apollo 10's speed, the journey to Alpha Centauri takes over 100,000 years. The fastest launch ever achieved was the New Horizons probe in January of 2006, thrown toward Pluto at about 16 kilometers per second, and it still needed 9.5 years just to reach Pluto. Chemistry got us the moon. Chemistry will never get us a star. This isn't pessimism, it's arithmetic, and every rocket engineer alive would tell you the same. So you reach deeper into the drawer. Ion engines. These are real, and they're beautiful. Instead of burning fuel, an ion engine takes a gas like xenon, strips its atoms into charged particles, and accelerates them with electric fields, spitting them out the back at enormous speed. The push is almost comically gentle, about the force of a sheet of paper resting on your palm, but it can sustain that push for years, and years of gentle pushing add up. NASA's Dawn spacecraft used ion engines to do something no other mission has done, orbiting one body in the asteroid belt, leaving it, and orbiting another. Ion propulsion is the future of moving around the solar system, and after every optimistic projection is granted, its realistic cruising speeds remain under about 100 kilometers per second. The trip to Alpha Centauri at that pace is still more than 12,000 years. The gentle engine run flawlessly for longer than any machine has ever run, delivers your great-grandchildren times 400 to a star their ancestors chose for them. Next draw. Nuclear power is where the numbers finally start to move, and it's also where the story develops a strange, melancholy history. Because the most serious interstellar engine designs humanity has ever produced are decades old, and they live on paper. In 1958, some of the best physicists in America, including the great Freeman Dyson, began work on something called Project Orion. The idea sounds like madness and was completely serious. You build a massive ship, thousands of tons, and behind it you mount an armored plate on shock absorbers. Then you throw nuclear bombs out the back, one after another, and ride the explosions. Detonation, push, detonation, push, thousands of times. The physics checked out. The calculations suggested an Orion ship could reach perhaps 3 to 5% of the speed of light, which would put Alpha Centauri about a century away, a long human project, but a human one, something a civilization could actually do. Orion was killed in 1963, not by physics, but by a treaty, the Partial Test Ban Treaty, which outlawed nuclear detonations in space, and by the reasonable fear of launching thousands of atomic bombs through the atmosphere. The one propulsion concept from the 20th century that could have touched the stars within centuries was set aside, and no one has picked it back up. In the 1970s, the British Interplanetary Society tried the next idea, fusion, in a legendary design study called Project Daedalus. Daedalus was an uncrewed starship powered by fusing tiny pellets of deuterium and helium-3, detonating them 250 times every second in a magnetic combustion chamber, and it was designed to reach about 12% of the speed of light. The catch is everything else about it. The ship would have weighed 54,000 tons, most of it fuel, roughly the mass of an aircraft carrier, assembled in orbit. And its fuel, helium-3, barely exists on Earth. The study proposed mining it from the atmosphere of Jupiter with floating robotic factories. None of this violates physics. All of it simply requires a civilization operating at a scale that makes our entire present space program look like a rowboat. And there's a detail about Daedalus that tells you everything about interstellar distances. Even that ship, the 54,000-ton fusion torch built by planet-scale industry, was a flyby mission. It couldn't stop. It would have spent 50 years crossing to its target star, and then swept through the whole system in a matter of hours, cameras running, falling onward into the dark forever, its mission complete after half a century in the form of a single family photograph radioed home. You've probably noticed the pattern by now. Each engine is more powerful than the last, and each one dies on the same hill. And the hill has a name: energy. Here's the brutal accounting that governs all of it. The energy of motion grows with the square of your speed. Double your speed and you need 4 times the energy. And the speeds we're discussing are not double anything. They're hundreds of times beyond our fastest machines, which means the energy requirements aren't hundreds of times larger. they're tens of thousands of times larger. Accelerating a single kilogram, one bag of sugar, to just 1% of the speed of light takes about as much energy as a small atomic bomb releases. 1 kilogram, 1%. Now scale it up. A useful robotic probe, something like the size of the spacecraft we send to Saturn, brought up to 10% of light speed, requires energy in the range of a large nation's total output. A crude ship, with its shielding and food and water and living space, thousands of tons of it, brought to a speed where the crossing takes 1 lifetime instead of 1,000, needs energy comparable to the entire output of human civilization. All of it. Everything. Every power plant and engine on Earth, dedicated to one departure. And then, if you'd like to slow down at the far end, rather than screaming past the nearest star after millennia of travel, you need to spend almost as much again, and you need to have carried the means of spending it with you the entire way. That last point deserves a moment of quiet respect, because it's the cruelest rule in all of rocketry. It's called the rocket equation, worked out by a deaf Russian schoolteacher named Konstantin Tsiolkovsky more than a century ago, and it says this: fuel has to carry fuel. Every kilogram of propellant you'll need at the end of the trip must be accelerated at the beginning of the trip, which takes more propellant, which itself must be accelerated. And the requirement doesn't grow gently, it grows exponentially. Push the speeds up toward interstellar territory, and the equation turns comic. The ship becomes a fuel tank with a closet attached, then a fuel tank the size of a mountain. Then, for some combinations of speed and engine, the mathematics quietly informs you that the fuel required exceeds the mass of the Earth. The universe never posts a sign that says forbidden. It just lets the numbers grow until the sign isn't necessary. There is one more engine in the drawer, the deepest one, the one science fiction reaches for: antimatter. And it's real. When a particle of matter meets its twin of antimatter, both vanish entirely, and every gram of their combined mass becomes pure energy. The most perfect conversion physics allows. A few dozen kilograms of antimatter would, in principle, drive a ship to a healthy fraction of the speed of light. Here's the situation with antimatter. We can make it. Particle accelerators produce it routinely, one particle at a time. The total quantity humanity has ever produced in every laboratory on Earth combined across all of history is measured in billionths of a gram, and the estimated cost of producing a single gram with present methods runs to many trillions of dollars. And if you had it, you couldn't set it down anywhere because antimatter annihilates on contact with any normal matter at all, including the walls of any container you build for it, so it must be held in magnetic suspension in a vacuum, without 1 microsecond of failure for decades, while containing the energy equivalent of thousands of nuclear weapons. One flicker of the power supply, and the ship simply becomes a very brief, very bright new star. Antimatter is not an engine we don't have yet. It's an engine that belongs to a species centuries more capable than us, if it belongs to anyone at all. So stand back from the drawer for a second, because the inventory is complete, and the shape of it is worth seeing whole. Chemical rockets, our entire crude spaceflight heritage 100,000 years to the nearest star. Ion drives, our finest operational deep space engines, 12,000 years. Nuclear pulse propulsion, a century, and it was outlawed before it was built and has stayed on paper for 60 years. Fusion, 50 years one way as a flyby, requiring an aircraft carrier's massive fuel mined from Jupiter. Antimatter, in principle, magnificent, in practice a substance we possess in billionths of grams. Nothing on this list is fiction. These are the real engines of a real civilization, ranked by ambition, and the gap between the bottom of the list and the top is a factor of 1,000, and even the top of the list strains against the distance and barely dents it. The nearest star does not care how clever we are. It sits behind an energy requirement the size of our whole civilization, and it has all the time in the world. And suppose for the sake of the night we solved it anyway. Suppose some future breakthrough hands us the engine, the energy problem cracked, the price paid. Here's the quiet second act of the problem that almost nobody talks about. Even with a perfect engine, the ship itself becomes the enemy, because no machine we have ever built can survive the crossing. Every machine ages. Metals fatigue and grow brittle under radiation. In hard vacuum, polished metal surfaces pressed together will slowly weld themselves into one piece, a phenomenon called cold welding that spacecraft engineers design around with coatings and ceramics. Lubricants creep and evaporate, plastics crumble. Electronics suffer a constant invisible rain, cosmic rays punching through circuit boards and flipping bits in computer memory, one here, one there, small corruptions that redundancy can catch, until the day the error lands somewhere unrecoverable. Our most durable spacecraft ever, the Voyagers, are dying of exactly this kind of old age right now. Their instruments have been shut down one by one to save power. Their thrusters have slowly clogged with residue after decades of firing. Their computers, marvels of the 1970s, hold less memory than a single photograph on your phone. And engineers perform surgeries across a full light day of distance to keep them whispering. They are 50 years old, our champions of endurance, and they're barely alive. The crossing to Alpha Centauri at their speed asks a machine to stay alive 1,500 times longer. Power is its own quiet death sentence. The Voyagers run on radioisotope generators, little hearts of plutonium whose warmth becomes electricity, and plutonium has a half-life of about 88 years, which means the heart weakens by almost 1% every year, relentlessly, no matter how well everything else is engineered. Within decades, not millennia, any such generator fades below usefulness. Solar panels are worthless out there because between the stars there is effectively no sun. A fission reactor needs fuel, coolant, and maintenance measured across centuries. Nothing on the shelf keeps a machine warm and awake for even 1,000 years of interstellar night, let alone 75. Whatever crosses that gap must be a machine of a kind that has never existed, one that repairs itself part by part, failure by failure, for longer than civilizations last, alone in the cold, with no spare parts arriving, and no engineer's hands ever touching it again. Then there's the matter of what the ship runs into, because the emptiness we admired earlier stops being philosophical and starts being ballistic the moment you move fast. Space between the stars isn't perfectly empty, it's just very thin, a fine mist of hydrogen atoms and, here and there, grains of dust smaller than smoke. At Voyager's gentle speed, they patter harmlessly. But energy grows with the square of speed, and at the speeds that make the trip worth taking, the mist becomes gunfire. At 10% of the speed of light, a dust grain with the mass of a bacterium strikes like a rifle bullet. A grain the size of a sand speck, the kind you'd never feel on your skin, hits with the energy of a truck bomb. Over light years of travel, statistics guarantee such meetings. So the ship needs armor, thick shielding out front, or a way to spot and dodge specks of dust at closing speeds of 30,000 kilometers per second. And armor is mass. And mass, as the rocket equation taught us, is the one thing you cannot afford. The faster you go to shorten the trip, the more violent the void becomes, and the heavier your shield, and the more fuel the shield demands, and the equation tightens around you like a knot. For a crewed ship, it tightens further, because the same thin rain that flips bits in computers shreds the genetic material inside living cells. Between the stars, there's no planetary magnetic field, no atmosphere, nothing between soft, human bodies and the galaxy's radiation, but whatever tonnage of shielding the mathematics grudgingly allows. Every path through the problem crosses the same toll booth, and the toll is always paid in mass, and mass is always paid in energy, and the energy was already impossible. Even aiming is harder than it has any right to be. Alpha Centauri isn't sitting still waiting for us. The whole system is sweeping through space at more than 20 kilometers every second relative to the sun. So a ship doesn't fly to where the star is, it flies to where the star will be in 75,000 years. A point far from tonight's position, leading the target the way a hunter leads a bird, except the flight of this arrow outlasts the species that loosed it. Get the aim wrong by a hair at launch, 1 degree of error, a fraction of a fraction, and it compounds across 40 trillion kilometers into a miss measured in multiples of the whole solar system. Course corrections need working thrusters and working sensors and remaining fuel in Millennium 10 and Millennium 50 on a machine whose builder's language no longer exists. And should the ship, against all of it, arrive with its systems breathing, one task remains, the one Daedalus surrendered on: stopping. Braking from interstellar speed takes roughly as much violence as achieving it. There are elegant paper schemes, vast magnetic sails that drag against the thin plasma between the stars, mirrors that break against the destination star's own light in the final years, and they're clever and unproven, and each adds tons of hardware that must have survived unused and perfect across a gulf of time deeper than recorded history, ready to perform flawlessly on arrival day at a star no engineer alive has ever seen. Stack it all up: the engine, the aging, the power, the dust, the aim, the brakes, and you begin to see the true shape of the problem. It's not one wall, it's a corridor of walls, each one behind the last, and the toll gets paid again at every gate, and the currency is always the same: energy, mass, and time. The three things the distance has already taken from us in full. And yet, one time in living memory, serious people with serious money looked at that wall and genuinely tried to find a door. The story of what happened to them is the most honest chapter in tonight's journey, so it deserves telling properly. In April of 2016, at a press event in New York, the billionaire investor Yuri Milner stood beside Stephen Hawking and announced a project called Breakthrough Starshot, with $100 million of initial funding and a goal that made headlines around the world: reach Alpha Centauri, not in millennia, within a generation. The plan was the cleverest end run around the rocket equation anyone has proposed because it simply refused to play the game. The rocket equation punishes you for carrying fuel, so Starshot's ships would carry none. The engine would stay home. Here's how it was meant to work. You build the spacecraft tiny, and I mean tiny, not the size of a car or a shoebox, but the size of a postage stamp, a single gram of electronics, a camera, a processor, a transmitter printed onto a chip, attached to a light sail a few meters across and thinner than a soap bubble. Then, in a high desert somewhere on Earth, you build the real machine, a phased array of lasers with a combined power of 100 gigawatts, roughly the output of 100 large power plants focused into a single beam. You loft the little chip into orbit, unfurl its sail, and for 10 minutes you pour that beam onto it. Light itself pushes. The pressure of photons on the sail, gentle as breath applied at that scale, accelerates the craft at tens of thousands of times Earth's gravity. And in those 10 minutes, the chip reaches 20% of the speed of light. 20%. 60,000 kilometers every second. At that speed, the crossing to Alpha Centauri takes about 20 years. A probe launched in 1 decade phones home in the 3rd decade after that, the signal itself taking 4 years and 3 months to limp back. A person could, in 1 working lifetime, sign the proposal, watch the launch, and hold the picture. For a moment, that was on the table. Stay aboard that little chip for a minute, because no vehicle ever conceived has a stranger ride. At 20% of light speed, the gentle emptiness we drifted through earlier turns hostile. Each stray atom of interstellar hydrogen strikes the sail like a subatomic bullet, and a mote of dust, a real speck, the kind that floats in a sunbeam, carries the punch of an artillery shell. The chip crosses the orbit of the moon within seconds of the laser shutting off. It passes Voyager 1, 50 years of human striving, on its first afternoon. And then, like everything else on this journey, it goes quiet, falling for 20 years through the dark with no engine to fire and no way to steer, aging alone, its designers aging with it. When Alpha Centauri finally arrives, it arrives all at once. The star system that took 2 decades to reach is crossed in hours. The chip sweeping through at 60,000 kilometers per second with no possibility of slowing, its camera snapping furiously at planets it will never see again. And then it's over. The nearest star dwindling behind it, the little emissary sailing on into a night that never ends, transmitting its photographs backward at a fraction of a watt, a whisper across 4 light years, the entire scientific payoff of the grandest engineering project ever attempted, contained in a stream of data thinner than a dial-up modem, arriving at Earth years after the encounter it describes. That was the plan, and I want to be fair to it because the physics was real. No law of nature forbids any part of Starshot. Every piece, the lasers, the sails, the gram-scale electronics, exists today in some early form. The people involved were not dreamers. They were some of the most capable physicists and engineers alive. And here's what happened. As of September of 2025, the project is on indefinite hold. Of the $100 million pledged, only around $4.5 million was ever actually spent. No sail was ever tested at meaningful power. No chip was ever launched. The meetings grew rarer, the funding quieter, and eventually the whole thing faded without so much as a press release to mark the end. The boldest interstellar project in human history, dissolving not with a failure, but with a shrug. The detailed studies had shown what the detailed studies always show. The laser array alone would demand a meaningful fraction of a continent's electrical output and decades of construction. The full program would cost not millions, but tens of billions at minimum. And at the end of all of it, success meant a few photographs of the nearest star taken in passing by a machine the size of a stamp. It turned out that even the cheapest possible ticket to Alpha Centauri, the most ruthlessly minimal mission human ingenuity could devise, 1 gram, one way, no brakes, was still too expensive for the richest civilization this planet has ever hosted. That's not a story about one project, that's the distance, introducing itself, which brings us, finally, to the version of this journey everyone secretly means when they ask the question, never mind the chips and the flybys, could people go? Could human beings in some century board something and cross to the nearest star? For that, since no engine we can foresee makes the trip in one lifetime, you must build the only kind of ship that works at walking pace, a generation ship, an ark. A sealed, self-sufficient world, launched knowing that everyone aboard will die aboard, and their children will die aboard, and their grandchildren after them, dozens of generations living and dying in a metal valley between 2 shores, so that strangers descended from the crew can someday step onto a world the founders chose. The idea has haunted science fiction for a century. It's beautiful and terrible in equal measure. And when you examine it closely in the light of actual biology and actual sociology, it may be the most fragile machine ever imagined. Start with the body count, in the coldest sense. Population geneticists have studied how many people a sealed ark needs to stay biologically healthy across centuries, avoiding inbreeding and preserving enough diversity to survive disease. The optimistic studies, assuming strict, managed reproduction for the entire voyage, land in the low hundreds. The cautious ones say 500, 1,000, more. So, picture the reality behind those numbers. A town sealed in a can forever. Every person aboard has their partner options constrained by a genetics algorithm, every birth scheduled to keep the bloodlines braided, generation after generation, with no exceptions and no appeals, for longer than most religions have existed. Now feed that town. The ship gets no resupply, ever. So it must be a working biosphere, recycling every breath, every drop, every scrap, with almost perfect efficiency for millennia. The International Space Station, our masterpiece of closed-loop engineering, recycles most of its water and still depends on cargo launches every few months. The most famous attempt at a fully sealed ecosystem, Biosphere 2 in the Arizona desert, enclosed 8 people in the early 1990s with every advantage: sunlight, a planet's gravity, rescue 1 phone call away, and within 2 years the oxygen level had fallen so far that outside air had to be pumped in to keep the crew safe. 2 years on Earth with help available. The Ark needs to outperform that by a factor of thousands in the dark, alone, without a single unrecoverable failure, not one in 10,000 years. And the machinery is honestly the easy part, because the cargo that actually breaks is human. A generation ship isn't a vehicle, it's a civilization, and civilizations change. Consider what a few centuries do to any society, to its languages, its faiths, its politics, its sense of what matters. Now run that forward across the 2,500 years our record speed ship spends just crossing the Oort cloud, and ask the uncomfortable questions. What happens when a generation born aboard decides the mission is a founding myth, no more binding than any other old story? What happens when a movement arises that wants to turn the ship around, or stop maintaining the engines, or worship them? Whoever arrives at Alpha Centauri, dozens of generations downstream, will not speak the language of the launch, will not share its beliefs, and may not remember in any meaningful way what the journey was for. Language alone would drift beyond recognition. English of just 6 centuries ago is nearly a foreign tongue to us, and the Ark's crossing is many times that long, sealed off from every outside voice that keeps a language anchored. Children born in the 200th generation aboard would grow up knowing the ship as the world, its corridors as geography, its maintenance schedules as seasons. Earth, for them, would be what Atlantis is for us, a story about a place that supposedly sank beneath the sky. And here's the twist the mission planners fear most. When the destination finally swells in the windows, why would the ship's people go down to it? They'd be asked to abandon the only world their line has known for millennia, a warm, working home, to descend to a raw and dangerous planet because of a promise made by ancestors so remote they've become characters in scripture. Arrival, the entire point of the voyage, might feel to the arrivers like exile. A generation ship doesn't just have to keep its passengers alive, it has to keep a purpose alive, undamaged, through more human turnover than any idea in history has ever survived. And beneath all of it lies an ethical problem with no clean answer. Every child born aboard is conscripted. They never chose the ship, and they can never leave it. And their entire existence, from first breath to last, is spent in transit between two worlds they'll never touch, because people they never met made a decision before their great-great-grandparents were born. We have never built a society that stayed stable for 1/10 as long as this voyage requires. The Ark doesn't ask for better engineering, it asks for better humans, and it has no way to make them. At this point, the science fiction shelf offers its favorite escape hatch. Fine, don't stay awake for the trip, sleep through it, freeze the crew, dim the lights, and let the ship carry a cargo of dreamers instead of a civilization. It's a lovely idea, and it's worth being honest about where it actually stands. The gentler version, hibernation, is real science with real research behind it. Hospitals already cool patients by a few degrees to protect the brain during surgery, and researchers funded by space agencies have studied stretching that kind of induced torpor from days toward weeks for a Mars run. Weeks. The gap between weeks and millennia is not a matter of refinement, because even in deep torpor, the body still burns fuel, still ages, still needs water, and waste handling, and muscle and bone that don't quietly dissolve and still soaks up cosmic radiation year after year, asleep or not. The harder version, true freezing, runs into water itself. When cells freeze, the water inside them forms crystals, and the crystals shred everything. Science can vitrify embryos and thin tissues, turning them glassy without crystals, but nothing remotely like a human organ, let alone a brain, has ever been frozen and brought back. No human being has ever been placed in suspended animation and revived. Not once, not for a minute. And notice the quieter problem underneath. Even if the sleepers could keep, the ship still can't. Every failure we counted earlier, the fading power, the aging metal, the dust, the millennia of maintenance with no hands available, all of it still applies, except now nobody's awake to fix anything. Sleep doesn't shorten the voyage. It just changes who fails first, the cargo or the vessel. There's even a strange mathematical trap waiting for anyone bold enough to launch early, and it has a name: the weight calculation. Suppose your generation ship departs this century at some heroic fraction of 1% of light speed, committed to its multi-thousand-year crossing. Meanwhile, back home, technology keeps moving. A few centuries later, a faster ship launches, and a few centuries after that, a faster one still. Run the numbers and the conclusion is deeply strange. Each of those later ships overtakes the earlier ones mid-flight. The pioneers who sacrificed most arrive last to a world their descendants may have already settled, greeted at the dock, if anyone remembers to greet them, as living museum pieces, the crew of a ship that history lapped. Which means that at any given moment, the truly rational choice is to wait for better engines, and the moment never obviously arrives when leaving beats waiting. It's not only that we can't go, it's that even when we barely can, going may never quite make sense. The distance doesn't just defeat our machines, it defeats the decision to try. There's one more cost of the distance that no engine, however magnificent, can ever pay down, and it may be the loneliest fact of the whole night. Even if every problem we've talked about were solved, the energy, the shielding, the arc, the arithmetic of generations, anyone who makes this crossing severs themselves from the human conversation in a way no traveler in history ever has. The reason is simple and absolute. Information itself is limited to the speed of light. From Alpha Centauri, a radio message home takes 4 years and 3 months. The answer takes another 4 years and 3 months. Ask a question, and the reply arrives in the 9th year. That's not a bad connection. That's the best connection physics permits ever for anyone, no matter what they invent. Feel what that would actually mean. The Apollo astronauts, standing on the moon, farther from home than anyone before them, spoke with Houston across a delay of 1 1/3 seconds, just enough to notice, not enough to matter. A future crew on Mars will wait up to 20 minutes for each reply, so no more conversation, just messages, like letters that arrive within the hour. Strange, but workable. Now stretch the same thread to the nearest star. A crew at Alpha Centauri that suffers a crisis, a failing reactor, a sickness spreading, a decision too heavy to make alone, can ask Earth for help and will hear the beginning of an answer 8.5 years later. Whatever happens, they are the only humans who can respond to it. Every emergency is theirs alone. Every judgment call is final. Mission control is a memory. And the mail that does arrive is time-traveled. News from Earth is over 4 years stale on delivery, answers to questions long since resolved, condolences for griefs already grieved. A parent's voice arrives after the parent is gone. The travelers wouldn't just be far from home in space. They'd be adrift from it in time, receiving the past on a delay and shouting into a future they can't quite reach. The most isolated human beings who have ever existed, by a margin that makes every previous isolation, every polar hut and every raft look like a crowded room. If you want to know what we'd look like from out there, from the far end of that broken thread, there's a photograph that answers it, and it wasn't even taken from very far away. On Valentine's Day of 1990, As Voyager 1 climbed toward the edge of the planets, engineers turned its camera around for one last look home, at the request of the astronomer Carl Sagan. From 6 billion kilometers, a distance our Tonight ship covers in its first year, Earth showed up as a fraction of a single pixel, a pale blue point caught in a stray beam of scattered sunlight, so small that if you didn't know which speck to love, you'd never find it. That became the most famous photograph in the history of spaceflight, and here's the part that belongs to Tonight. It was taken from less than 1/10,000th of the distance to Alpha Centauri. From the nearest star, Earth isn't a pale blue dot. It's nothing. No telescope we have ever built, pointed back at us from a world around Proxima, could pick our planet out of the sun's glare and say with confidence that anyone lives here. Our oceans, our cities, every light we've ever burned, all of it vanishes into the brightness of one ordinary yellow star among thousands. If there are astronomers on some twilight world 4 light-years away running their own version of Tonight's story, they know our sun well. It's one of the brightest stars in their sky. They may have measured its steadiness and put it on their short list of suns worth watching, but us, the noise and grief and music of 8 billion people, they cannot see at all. The distance hides us as completely as it hides them. 2 porch lights facing each other across an ocean, each wondering if the other is a lamp in a window or just another wave catching the light. So that's the journey, and everything about it says the same quiet word. And now I want to turn the telescope around, because here is where Tonight's story earns its strangest twist. All night we've talked about Alpha Centauri as a distance, a gap, an impossibility. But it's not an abstraction. It's a place. It has geography and weather and worlds, and here's the astonishing part. We know it does, in detail, right now, without ever having gone. So before we finish, let's spend some time where the ships can't take us and see what's actually waiting on the far shore. The first surprise is that the nearest star isn't a star at all. It's 3 of them, a family, gravitationally bound, and each of the 3 is a different kind of beautiful. The heart of the system is Alpha Centauri A, and A is the closest thing to a mirror of our sun that the nearby galaxy offers. The same type of yellow star, slightly heavier, a little brighter, shining that same white gold light that's falling on your street in daytime. If you stood on a world beneath Alpha Centauri A, the daylight would feel like home. Circling it in a slow 80-year embrace is Alpha Centauri B, a touch smaller and cooler, glowing amber orange. The 2 swing between roughly the distance of Saturn and the distance of Neptune from each other, close enough that from a planet around one, the other would blaze in the night sky hundreds of times brighter than our full moon, a second sun in miniature, bright enough to read by, bright enough to cast crisp shadows at midnight. Imagine that for a moment, evenings with 2 sunsets. First, the great yellow sun going down in fire. Then hours later, the brilliant orange spark of its companion sinking after it, and a kind of second dusk falling twice in one night. That sky exists. It's real. And it's happening tonight, 4 light years from your pillow. And then there's the third member of the family, the runt and the champion. Far out from the bright pair, about 13,000 times the Earth-Sun distance, drifts a dim red ember called Proxima Centauri, so small and faint that no human eye can see it unaided, even though it is, right now, the closest individual star to us of all. Proxima is a red dwarf with about 1/8 of the Sun's mass, glowing mostly in dull red and infrared light. It circles the bright pair once every 550,000 years or so, on an orbit so wide and slow that astronomers only confirmed it was truly bound to them in 2017. Here's a fact worth carrying to sleep. Red dwarfs like Proxima burn their fuel so slowly that they live almost forever. Our Sun has perhaps 5 billion good years left. Proxima will still be quietly glowing trillions of years from now, thousands of times longer than the universe has yet existed. The nearest star to Earth tonight will outlive the Sun, and every star you can see, and it will still be shining when every one of them has gone dark. Now come in closer, because the worlds are there too. In August of 2016, a team led by the astronomer Guillaume Anglada Escude announced something extraordinary. Proxima Centauri, the closest star, has a planet, and not a distant, frozen giant, but a rocky world at least as massive as Earth, orbiting in the star's habitable zone, the band where liquid water could, in principle, survive on the surface. They named it Proxima b, the closest star in the entire sky, and it turns out to keep an Earth-sized planet in the one orbit where water might flow. Since then, the family has grown. A second, smaller world, Proxima d, barely a quarter of Earth's mass, was confirmed in 2022, skimming around the star in just 5 days, and evidence points to a possible third, larger and farther out. Understand what this means. We didn't have to cross the void to learn any of it. Astronomers measured the star's tiny wobble, a shiver of about a walking pace in Proxima's motion, from telescopes in Chile across 40 trillion kilometers, and read the presence of worlds in it. The nearest star system has planets, plural, and one of them is the closest possibly habitable world that will ever exist for us, because nothing can ever be nearer. Before you fall in love with Proxima b, though, you should know what kind of neighborhood it lives in, because the truth is harsher and stranger than the postcard. Proxima b orbits its dim red star at only about 5% of the Earth-Sun distance, with a year lasting 11 days, and a world that closes almost certainly tidally locked, one face pinned forever toward the star, the other forever away. Half the planet lives in a single, endless afternoon, half in a night that has lasted billions of years, and the only gentle places, if there are any, lie along the twilight ring between them, a band of permanent sunset circling the entire world. And the little star is not gentle. Proxima is a flare star, racked by magnetic storms, and in March of 2016, astronomers watched it unleash a superflare so violent that, for a few minutes, this star, too faint to see, became briefly visible to the naked eye from Earth. For any atmosphere on the day side of Proxima b, eruptions like that, repeated over billions of years, are a slow sandblasting. Modeling published in 2018 suggested such flaring could strip a planet's protective ozone in mere years and erode whole atmospheres over cosmic time. So, Proxima b may be a bare rock, scoured and silent, or if it was born with a thick atmosphere or deep oceans, it may yet be a world of red twilight and heavy weather, sunsets that never end above seas that never freeze. We genuinely don't know. It's the nearest world that could hold water outside our solar system, and its true face is one of the great open questions in astronomy, sitting right there at the minimum possible distance, daring us. And the discoveries haven't stopped. In fact, the newest one may be unfolding this very summer while you're falling asleep to this story. In August of 2024, astronomers pointed the James Webb Space Telescope, the most powerful eye humanity has ever opened, at Alpha Centauri A, the sun-like heart of the system. Observing next to a star that bright is brutally hard, like photographing a firefly beside a lighthouse, so the telescope hid the star's glare behind a mask and stared at the darkness beside it. And there, in the mid-infrared, a faint point of light appeared where nothing should be. The measurements suggest a giant planet, something roughly the mass of Saturn, orbiting Alpha Centauri A at about twice the distance from the Earth to the Sun, which would place it inside that star's habitable zone. Not a world for life as we know it. Gas giants have no surface to stand on, but think about what it would mean. A giant planet circling the nearest sun-like star in the warm zone. And if it's there, it could have moons, and moons of warm giants are among the most tantalizing places in all of astronomy. The detection echoed an earlier hint seen from a telescope in Chile back in 2019. Two glimpses, 5 years apart, of something pale circling our nearest solar twin. But here's the part that makes it a proper mystery. When the Webb team looked again, in February and April of 2025, the point of light was gone, vanished. Now, a vanishing isn't necessarily a disproof. The astronomers ran thousands of simulated orbits, and in many of them, the planet simply spends those months too close to the star's glare to be seen, hidden in the lighthouse beam. The two papers describing all of this were accepted by a major astronomy journal in 2025, with the candidate labeled exactly what it is: unconfirmed, promising, maddening. And if the astronomers sound almost painfully careful, they've earned that caution the hard way, because Alpha Centauri has fooled us before. In October of 2012, a European team announced what seemed like the discovery of the decade: an Earth-mass planet orbiting Alpha Centauri b, found by teasing a tiny wobble out of years of exquisite measurements. It made front pages around the world. The nearest star system had an Earth-sized world, textbooks were ready to be rewritten, and then, over the following 3 years, other astronomers reanalyzed the data, and the planet simply dissolved. The signal turned out to be a ghost, an artifact of how the observations happened to be scheduled, a pattern in the noise that looked like a world. By 2015, it was gone from the catalogues, one of the most famous planets that never existed. The lesson stuck. At the very edge of what our instruments can do, which is exactly where the nearest stars keep us working, the universe sometimes hands you a mirage, and the only cure is patience and another look. And the story has a date attached. The orbital solutions say that if the planet is real, it should swing back out into view in August of 2026. That's next month, as I'm telling you this. Somewhere in the coming weeks, the Webb telescope is due to turn back to the nearest sun-like star and either find that little light again and hand humanity a confirmed giant planet next door, or find empty sky and send the astronomers back to their orbits and their doubts. Either way, you're living inside the answer's arrival window right now. The nearest star system is not a settled fact in a textbook. It's an active frontier, being mapped in real time this season by a telescope 1 million miles from Earth, staring at a light 4 years old. Hold that thought up against everything else we've learned tonight, because together they form the strangest truth of the whole story. We cannot go to Alpha Centauri. We've established that beyond much argument, not this generation, not the next, perhaps not any. And yet look at everything we know about it. We know the masses of all 3 stars and the 80-year waltz of the bright pair. We know Proxima's slow 500,000-year orbit. We found 1 planet, confirmed a 2nd, suspect a 3rd, and we're watching a possible 4th flicker in and out of view around the sun-like star this very summer. We can measure the wobble a small planet's gravity imposes on its star from 40 trillion kilometers away, a motion about as fast as you walking to your kitchen. In the coming years, telescopes now being built will read the atmospheres of nearby worlds like Proxima b, hunting for water vapor, for oxygen, for the chemical fingerprints of life, all without leaving home. Here's the comparison that puts it in one frame. The James Webb Space Telescope, the machine currently studying the nearest star system, cost about $10 billion. Breakthrough Starshot, the cheapest serious plan ever devised to physically touch that system with a single gram of hardware, was projected to need many times that, and it quietly died. Seeing is thousands of times cheaper than touching. It always will be, because the universe has a currency exchange built into its laws. Light is massless and travels at the cosmic speed limit for free. Matter is heavy and slow and pays the full exponential toll of the rocket equation for every gram. We live in a universe that hands out windows generously and doors almost never. Once you see that asymmetry, you start to see it everywhere, and it reframes what kind of beings we are. We are, and may always be, a species of watchers. We've mapped galaxies, billions of light years away that no probe of ours will ever approach. We've photographed the glow of the universe's own infancy, light older than the Earth, and we caught it with antennas without ever leaving our shore. The great bargain of astronomy, the whole magnificent enterprise, is built on accepting the photons and waiving the visit. And Alpha Centauri is where that bargain stings the most, because it's the one place where the visit feels like it ought to be possible. Andromeda is 2.5 million light years away, and nobody aches over not going. But 4.24 light years. The star you can see from a beach in the southern hemisphere, the system with the Earth-sized planet, the solar twin with the maybe giant swinging back into view next month. That one feels like it should be reachable, the way the far shore of a wide river feels reachable, and it isn't. And the feeling never quite goes away. The nearest star is close enough to break our hearts and far enough to keep them broken. And there's one more turn of the screw, the one the astronomers themselves think about late at night. Alpha Centauri isn't just a destination we happen to be missing. It's the easiest interstellar destination that will ever exist, the floor, the absolute minimum the universe charges for a ticket to another star. Every single other star in the galaxy costs more. The next nearest system beyond Alpha Centauri is Barnard's star at 6 light years, half again as far. Sirius, the brightest star in our sky, is 8.5 light years out, double the toll. The average spacing between stars in our quiet suburb of the galaxy runs 4 to 5 light years, and it only thins out from here toward the galactic rim. The Milky Way is 100,000 light years across and holds hundreds of billions of stars, and from where we sit, effectively all of them, every wonder, in every catalogue, every strange world the telescopes tease us with, sits behind a paywall steeper than the one we've spent all night failing to climb. If the nearest star demands 75,000 years of our best machine, the galaxy is not a place we live in. It's a place we live next to, one lit window in an unwalkable city, and Alpha Centauri is the house across the street, the one whose lights we can see from our kitchen, the neighbor we will spend our whole civilization waving to and never once visit. And yet, before you conclude that nothing ever crosses, the universe has been quietly making the point that the crossing is possible, just not for the likes of us. In October of 2017, a telescope in Hawaii picked up a small object moving through our solar system far too fast to belong to it. It was named Oumuamua, a Hawaiian word meaning something like a messenger from afar, arriving first, and it was the first object ever confirmed to have come from another star system entirely. A splinter of some other sun's family, hundreds of meters long, tumbling past our sun after a journey of unknowable length and gone again within months. 2 years later came a second visitor, a comet named Borisov, unmistakably interstellar, trailing gas made around another star. And in July of 2025, astronomers confirmed a third, a comet designated 3I Atlas, sweeping through on its own unrepeatable visit. 3 interstellar travelers in 8 years once we knew how to look, which suggests such wanderers drift through constantly, unnoticed, ancient beyond guessing. Nature, it turns out, sends things between the stars all the time. It just does it the only way the distance allows, with dead rock and patient ice, no passengers, no schedule, and no need to arrive anywhere in particular, ever. The gap we can't cross is being crossed tonight in both directions by things that gave up nothing to make the trip because they were never alive, never in a hurry, and never coming back. Since the ships can't carry us, let the imagination make one last landing before we turn for home. Come stand, just for a few minutes, on the world next door. You're on Proxima B, somewhere along the twilight ring, that band of permanent evening between the day side and the night side. The ground under your boots is dark rock, old beyond anything on Earth, and the light is the first thing you'd never get used to. The sun of this world hangs low and enormous near the horizon, and it doesn't move. It hasn't moved in 1 billion years. Proxima appears nearly 3 times wider in this sky than our sun does in ours, because the planet huddles 20 times closer to its star than the Earth does to home, and it glows a deep sunset red. Not the red of a poster or a filter, but a heavy, banked fire crimson that leaves the sky the color of embers and wine. Shadows here are long and permanent, painted onto the landscape. Walk toward the light, and the land slowly brightens into a scorched noon that never ends. Walk away from it, into the dark half, and within a few 100 kilometers you'd cross into a night billions of years old, where the frozen ground has never once seen its own star, and the sky belongs entirely to everyone else's. And in that eternal night, one star among the thousands would catch your eye, a bright yellow-white one, easily among the brightest in that sky, but otherwise ordinary. That's the sun. That unremarkable point of light is every ocean, every city, every voice, every grave, every night you've ever slept through, all of it together, small enough to cover with your fingertip held at arm's length. From the nearest world of another star, home is just a star too. If the sky here decided to perform, you might see Proxima flare, the little red sun abruptly flashing brighter, washing the twilight in violet white for a few minutes while the magnetic storm rages, and you would want good shielding over your head. And on some worlds of this system, remember, there are 2 other suns in the sky. From a moon of that possible giant planet around Alpha Centauri A, you'd live beneath a warm yellow sun, nearly the twin of ours. Watch a brilliant orange companion star wheel through its 80-year dance, and find dim red Proxima only if you knew exactly where to look. 3 suns, 1 family, and every one of those skies is real, hanging right now above landscapes no one has ever seen. In the one star system in all the universe that will ever be closest to us. That's what's actually across the gap, not an abstraction. Weather and rock and red evening light 25 trillion miles from your bedroom. patient as stone. So let's ask the question in the title honestly one last time, with everything on the table. Never is a heavy word, and I've used it all night, and you deserve to know exactly how much of it is physics and how much is confession. Here's the truth. Physics does not forbid the crossing. There's no law of nature with our name on it barring the way. The speed of light is a wall, but we don't need light speed. 10% would do it in under half a century, and no equation anywhere says a machine can't move that fast. What stands in the way isn't a prohibition, it's a price. Energy on the scale of an entire civilization's output, engineering that must run flawlessly for decades or millennia, and a species willing to spend a large share of its total wealth on a voyage whose reward is knowledge and whose return, if any, arrives generations after the spenders are gone. The universe never said no. It just posted a price so high that every generation so far, upon reading it, has quietly put the ticket back on the counter. So when tonight's title says we'll never reach the nearest star, understand it precisely. Never, at any speed we've flown, by a factor of thousands. Never, with any engine we've built or funded. Never, for you and me and everyone breathing tonight, with a certainty that no optimism can dent. Whether it's never for our species entirely depends on beings we haven't become yet, on a civilization richer, more patient, and more unified than any that has existed, and the honest answer to whether that civilization will ever exist is that nobody knows. The distance is permanent. Our smallness might not be. You might be waiting for me to mention the shortcuts, so let's give them their minute, honestly. Yes, physicists have sketched ways to cheat the distance rather than cross it. There's a famous solution of Einstein's equations worked out in the 1990s describing a bubble that contracts space ahead of a ship and expands it behind. A warp drive in the full science fiction sense, and the mathematics genuinely allows it. What the mathematics demands as payment is the problem. A form of negative energy, matter that repels instead of attracts, which has never been observed in any usable quantity anywhere in the universe, and which early estimates suggested would be needed in amounts comparable to the mass of a planet. Wormholes carry the same fine print, shortcuts through space that stay open only if threaded with the same impossible substance. These aren't engineering projects awaiting funding. They're reminders that our map of physics has unexplored edges, and that if a true shortcut exists, it belongs to physics we haven't met yet. Not to physics we've merely failed to afford. Nobody can promise it's there. Nobody can promise it isn't. The honest ledger tonight has one column for what's forbidden, and it's nearly empty, and one column for what's priced beyond our reach, and that column holds everything. And if the crossing ever does happen, it almost certainly won't look like the science fiction we grew up on, a crew waving from a gleaming bridge. It will probably look like the star-shot chip's distant descendants, machines, small and patient and expendable, mines of silicon that don't age during a 40-year cruise and don't grieve the home they left, arriving in swarms, mapping those red twilight worlds and radioing back dreams 4 years old. Perhaps living minds follow eventually, or perhaps by the time anything of ours stands beneath those 3 suns, the word ours will have stretched to mean something we wouldn't recognize tonight. The first earthly thing to touch another star system will not be a person. It will be something we made, carrying something we wrote, and maybe that's fitting. We are, after all, the species that has always sent its words where its body couldn't go. Here's one more secret, saved for late in the night. The gap between us and Alpha Centauri, the terrible 40 trillion kilometers we've spent all this time measuring, is shrinking. The stars are not fixed. Every star in the galaxy is in motion, orbiting the galactic center, drifting past its neighbors like ships in a slow harbor. And Alpha Centauri happens to be moving gently toward us. Over the next roughly 30,000 years, the distance will close from 4.24 light years to somewhere near 3. Our descendants, if we have them, will inherit a nearest star measurably closer than ours, the ticket price marked down by a quarter, not through any effort of ours, simply because the harbor drifts. And then, over tens of thousands of years more, Alpha Centauri will sweep past its closest approach and begin to recede, and other stars will drift inward to take its title, and the sky your descendants navigate by will be a sky you'd need a map to recognize. Even Voyager 1 participates in this slow shuffle. Having left our harbor, it's fated to wander the galaxy essentially forever, and in about 40,000 years it will drift within less than 2 light years of a small red star called Gliese 445. A quiet flyby no one may ever witness, our first message in a bottle passing its first island unopened. On the timescales the stars actually live by, distance itself is weather. It changes. The gap we can't cross tonight isn't even the same gap our grandchildren's grandchildren will fail to cross. The universe rearranges the puzzle even as we sit staring at the pieces. Maybe that's the kindest way to hold tonight's story. We arrived, as a species, extraordinarily early. The universe is not even 14 billion years old, and red dwarfs like Proxima will glow for trillions. 99.9% of cosmic history hasn't happened yet. We are awake in the universe's first morning, standing on the shore of the first ocean we found truly uncrossable. And it's no failure to say the boats we've built so far are too small. The Polynesians who eventually crossed the Pacific were descended from people who, for thousands of years, could not, and who must have stood on their beaches at night looking at distant island glow they had no way to reach. There never lasted 100 generations, and then one morning it ended. Ours may last 1,000 generations, or 10,000, or it may simply be the truth of our kind forever, and we'll remain what we are tonight, the watchers, the measurers, the ones who knew their neighbors' 3 suns and 11-day years, and never once felt their warmth. Either way, No one can say we ignored the house across the street. We've counted its windows from our own dark yard. We've learned the names of everything we cannot touch. There are worse ways for a small species to spend its first morning. Now, as we finally come to the end of tonight's journey, let's gather it all up gently, the way you'd fold a map after a long trip. We left tonight on the fastest ship our species has ever flown, and we watched the solar system fall away in months. We passed Voyager 1 in year 5, half a century of human reach gone by in a moment. We learned the true size of the friendly little number, 4.2440 trillion kilometers, 2 basketballs an ocean apart with nothing in between. We drifted for centuries through the sun's own cometary halo and watched every institution and language we left behind dissolve in our wake. We opened the drawer of engines, chemical, ion, nuclear, fusion, antimatter, and we watched each one fall short by factors of thousands, defeated not by imagination but by the price of energy itself. We watched the boldest project of our age, a gram of silicon on a beam of light, quietly fold. We weighed the Ark and found the cargo, the human cargo, heavier than any engine could lift. And then we turned the telescope around and found the consolation hiding inside the sentence, because the star we can never reach turned out to be a place we know intimately. 3 suns in a slow embrace, a red twilight world at the minimum possible distance, and a ghost of a giant planet due to step back into the light next month. We can't touch any of it. We know almost all of it. Both of those facts somehow are true at once, and they will stay true for the rest of your life. And maybe that's the real lesson the nearest star has been teaching us all along, patient as stone, 4 light years from every bed on Earth. The distance taught us how to measure. When Henderson caught that tiny parallax shift and could hardly believe his own arithmetic, the distance taught us how to see, driving us to build eyes 1,000,000 miles out that can read the shiver of a small star from across the void. The distance taught us honesty every time an engine drawing or $100 million promise met the arithmetic and folded. And the distance taught us something about scale that no other fact in the sky teaches quite so personally. The universe is not hostile to us. It's simply built to a size that wasn't chosen with us in mind. And the first honest look at that size is not a defeat. It's the beginning of actually knowing where you live. Because here's the thing about the word never that tonight's title carries. Our never is real, but it's ours. It belongs to this century, these machines, this brief early morning of a species that only learned the distance to its neighbor 2 lifetimes of memory ago. In 1839, we discovered how far away the nearest star is. Less than 2 centuries later, we know its planets, its flares, its family, its future. That's the blink of an eye, cosmically, and in that blink we went from lights on a dome to reading the weather of other worlds. The gap is 40 trillion kilometers, and it took just 180 years to shrink from unknowable to merely uncrossable. What the next 180 years shrink it to is not something anyone alive tonight can say. So here we are, at the end of the crossing we could actually make, the one made of words and numbers and a couple of hours of night. Somewhere above the southern half of the world right now, Alpha Centauri is doing what it's done every night of human history, hanging there in the constellation of the Centaur, third brightest star in the sky, indistinguishable to the casual eye from every other star that's 1,000 times farther. Sailors steered by it before anyone knew what it was. Henderson measured it and sat frightened by the answer, and tonight it's shining on empty beaches and sleeping towns, and its light is falling, some of it, into the eyes of the few people still awake enough to look up. If you're ever under the southern sky, find it. It's not hard. It's the bright one near the Southern Cross, and when you look at it, remember what's actually happening in that moment. Photons that left a triple star system in the early part of 2022, that crossed 40 trillion kilometers of the emptiest nothing that exists, that outran every machine we've ever built by a factor of thousands, are ending their 4-year journey on the back of your eye. That's the crossing. That's the only crossing there is. The light comes to us because we cannot go to it, and every time you see that star, an arrival is happening, the universe completing the trip in the only direction it permits. Thank you for joining me tonight on this long journey to the nearest star, through the distance, the engines, the arcs, and the 3 suns waiting at the far side. If this exploration moved you or changed the way that little number 4.24 sounds in your head, a like or a subscribe genuinely helps these quiet nights continue, and it's always good to have you here. And if you're still awake, still drifting somewhere between the Oort cloud and morning, that's all right. There's no hurry now. The ship has no engine. The destination isn't going anywhere for 100,000 years, and neither are you. The nearest star will still be there tomorrow night and the night after, 4 years of light away, keeping its distance, keeping its worlds, keeping its patient red ember burning for a future longer than all the futures we can imagine. The house across the street has its lights on. We know the names of everyone who lives there, and someday, long after tonight, someone or something that remembers us may finally knock on that door. Until then, we watch and we wonder and we rest. Sleep well tonight, somewhere safe beneath the nearer sun. Good night.